Welcome back to Physics 152 Online. In this next section, we'll apply the information that we've learned about calculating electric fields and electric potential difference to study the properties of a special kind of electrostatic device. Some people call this, along with resistors and inductors, a passive circuit element, and that circuit element is the capacitor. So we'll begin discussing what we mean by capacitance, what it's useful for, and then how we can calculate the capacitance for certain special geometrical situations. So we start off by commenting that a capacitor is a device that consists of various kinds of conductors separated sometimes by an insulating layer whose function is to store charge and to allow us, when connected to a potential difference supplied by like a battery, also to store energy. So the idea is connecting the capacitor to a source of electric charge, such as a battery, allows us to store charge on the capacitor plates, and then when we disconnect it, that capacitor can be used as an energy source. Schematically, it might be illustrated like this. The most common way of thinking about a simple capacitor is looking at two parallel conducting plates that, when connected to a power supply, can store an amount of charge. And the plates will store in equilibrium equal amounts of charge, plus Q and minus Q. So the ability of a capacitor to store charge is quantified by the quantity that we call capacitance. Capacitance is defined as the absolute value of the ratio of the charge stored on the plates divided by the potential difference it took to put the charge on the plates. And the experimental observation that we make is that this ratio is a constant for a certain size and shape geometry of capacitor. So in other words, if you double the charge, you won't change the capacitance, because doubling the charge will simply be happening because the potential difference was doubled. So the capacitance is this constant ratio between those two quantities. The units, of course, if charge is in coulombs and potential difference is in volts, then a coulomb per volt is the unit for capacitance. We give that a special name in honor of Michael Faraday. We call that the farad. But it's important to realize that a farad is a really large value for capacitance, and the kinds of capacitors that you might find on an integrated circuit board inside some kind of electronic device often have values of capacitance that are microfarads or even nanofarads in some cases. So the value of the capacitance for a specific device depends on the size and shape of the conductors that are used, and also if there is an insulating material between the conductors, it depends on the property of that material. We can use Gauss's law to get really good approximations that lead to calculations for C that are in good agreement with experiment. We're going to use Gauss's law, and then we're going to use the definition of electric potential difference. So topics that came up in chapters, in the previous two chapters in our textbook, are going to be of direct application right here. And the steps are pretty simple. With a particular capacitor geometry, we just assume that we charge up the plates so that there's a charge plus and minus Q on the capacitor plates. Then we sketch the electric field lines and use Gauss's law to find an expression for the electric field in the region between the plates. Then we use the definition for electric potential difference and the electric field that we find in step 2 to calculate the potential difference between the two plates. And so that will give us Q, and then delta V will be in terms of Q, and when we take the ratio of those two, the result will be the capacitance for that particular geometry. So let's do an example. The classic case is a parallel plate capacitor, as I already mentioned. So let's assume two parallel plates that have an area A and a separation distance D. Find the capacitance. So our schematic here shows that we've already assumed a positive charge Q on the left plate, negative charge Q on the right plate, and that means that the field lines in between the plates will go from left to right. And Gauss's law allows us to calculate what the expression is for the electric field in that region. So the plates have area A and separation D, and we should expect to see those two quantities in our final result, because A has to do with the size and D has to do with the distance, or the geometry between the plates. The side view would look like this. Now what we want to do is find a Gaussian surface that will take advantage of that electric field symmetry and make it easy to calculate the flux integral that appears in Gauss's law. And we can either use a cylinder or we can use a cube. And so I'll just imagine that we have a cube that has one face inside the conductor on the left-hand side, the other face in between, which is the region where we want to find the field, and the other four sides of the cube have their surfaces so that the surface normal, dA, is perpendicular to the electric field vector, and that will make the flux integral really easy to evaluate. So for a cube, since the integral E dot dA is evaluated for a closed surface, the cube has 6 different surfaces, but for several of them the contribution will be 0, and that will make this an easy calculation to do. So for the left face over here, we know that the integral E dot dA on that surface is 0 because the electric field is 0 inside a conductor. Alright, for the right face it's easy because the electric field points in the same direction as the dA vector, and when we evaluate that integral, the dot product simply becomes E times dA, the E comes outside the integral, and then integrating over the surface area of that face of the cube, it just gives us its area. And I didn't mention this, but in my drawing, the Gaussian cube assumes that each square face of the cube has a surface area A0. So for the right-hand side, we will get a flux of E times A0, because E and dA, as I said, are parallel. The other 4 faces will give contributions equal to 0 because, for example, the top face has dA pointing up, E is perpendicular to that. The bottom face has dA pointing down, and again, E is perpendicular to that. So the other 4 faces don't contribute anything. And that means, on the left-hand side, all we have for that surface integral is just the electric field in between the plates times that surface area of the Gaussian surface, A0. The right-hand side is easy because these plates, if there's a certain charge Q on the plate and an area A, then charge per unit area, Q over A, multiplied by A0 tells us how much of the surface charge is enclosed by this Gaussian cube. So Q over A times A0 divided by epsilon 0, and when the smoke clears from this, we find an expression. E is Q over A times epsilon 0. So that's the first step. The second step now is to use the expression for E to calculate the potential difference between the two plates. And we know the answer is always going to be the same no matter what path we take to get from one plate to the other. So we choose the simplest path possible. And that simply is a straight line path parallel to the electric field going from the left plate to the right plate. What do we get if we calculate that potential difference? Well, the definition of potential difference minus integral E dot dL. If E and dL are parallel, this becomes E times dL. The E along that path, you'll notice from the expression that we plugged in for E, it doesn't depend on where you are. The electric field is a constant in that region. So along that entire path, E can come outside the integral, and we just replace it with the result from the previous slide, Q over A epsilon 0. The integral dL just captures the entire distance between the plates, which we've already said was d. So now we have a simple expression for delta V, and we are almost done. The capacitance is the ratio Q over delta V. Well, for the numerator, we just leave it as Q. Delta V in the denominator depends on Q. We plug that in, take the absolute value, so the minus sign goes away. The Q's cancel, as they should, and the result is epsilon naught A over D. And that is the simple expression for an empty parallel plate capacitor. So you see, as we mentioned already, it depends on the surface area and the plate separation distance. So the geometry, the size and shape of the plates is what enters into this result. Something similar can be done, and it actually is done, as examples in your textbook, for a two-dimensional capacitor, a cylindrical capacitor, and then for a three-dimensional capacitor, which would be the spherical geometry. So we'll move on next time to talk about the energy that's stored by a capacitor and also combinations of capacitors in electrical circuits. But I hope that's been a helpful introduction, and I will see you in class.